So what we're going to do now is we're going to turn our attention to the final paradigm in C++. So we've talked about the evolution of C++ and abstraction from the very simple styles of C-level information hiding and the somewhat problematic C-style data abstraction, which was clearly deficient and problematic and ugly. We've talked about the C++ data abstraction, which has been around since the beginning, and that certainly improves upon the C-style data abstraction. We've talked about generic programming, which is an improvement upon classic C++ data abstraction by making it possible to generalize on types. We've talked about exception handling, which isn't really a paradigm per se, it's just a way of being able to separate errors from normal processing. And now we're ready to talk about the final paradigm that's supported in C++, which is object-oriented programming. And it may seem funny that we're covering object-oriented programming at the end of the overview, given that C++ made its fame originally from being an object-oriented programming language 40+ years ago. But in fact, that's really the point. The object-oriented features in C++, while they do have their purpose, are really not the primary focus of modern C++ development. And I'll talk about object-oriented programming, then we'll talk about why it's been somewhat deprecated isn't quite the right word, but somewhat de-emphasized relative to generic programming. So before we start on this, let's kind of recap what the deficiencies were with our prior examples that use generic programming. So the main problem with our prior examples was that if we were to make any change to the implementation, if we wanted to go, for example, from an array implementation to a linked list implementation of our stack, we would have to go in and perform surgery on the code itself. So here's our stack, and if we wanted to change this from the array to a linked list, we'd have to go in and modify that code, and then we'd have to recompile it and relink it, and then tell the clients go ahead and relink with and recompile with a new version. And while that might or might not be the end of the world, especially in modern open source projects, it would be a pain if we were trying to do things like release to release binary compatibility, because you don't want people to have to go and recompile everything just to get a new version of something. That gets really old in a hurry. Moreover, if we wanted to make any changes, we'd actually have to have access to the source code. Now, in the case of the templates, we don't have much of a choice, because if you make changes to template code, or if you have template code, you have to get the source code. But again, it's often nice to be able to make changes to stuff without breaking or modifying or recompiling, relinking, and so on existing code. Just means one less thing to go wrong, one less level of complexity to integrate into your DevOps tool chain, and so on and so forth. So what are we going to do to solve this problem? Well, of course, the time-honored way to solve this problem in C++ is to combine inheritance with dynamic binding, and I'll talk about both of these concepts in a minute, in order to completely decouple the interface from the implementation and be able to do the selection of the implementation at runtime. So the fancy way of saying that is we're changing from static binding time, compile or link time, to runtime binding, which is dynamic binding. And to do this properly, we have to introduce the concept of C++ abstract base classes, or ABCs. And the example here on the right-hand side is just a little snippet of some code we're about to examine in more detail when we crank up the CLion IDE. And you'll see that it's going to define the interface for the stack without requiring any implementation whatsoever. And the clue that this is taking place is the =0 syntax at the end of the methods like push and pop and top and so on. So all those things will be methods that are going to be what are called pure virtual methods. And we'll talk about what those are in just a moment. Okay, so we're about to go take a look at the implementation of this stuff. But the key thing I want you to remember here is that object-oriented programming is designed to enable runtime binding of method calls. And with that comes a degree of freedom and a degree of separation of concerns that is not there with the more traditional generic programming techniques. Now, you'll also notice for this example that I've combined object-oriented programming and generic programming and exception handling. So it's going to do all the same things we saw before, except it's going to allow dynamic binding. So let me now go ahead and try to get my editor up. And to do this, I'm going to stop sharing. And then I'm going to go back and reshare. Whoops. Hold on. All right. I'm going to stop sharing. I'm going to get out of PowerPoint, which I think I did. Yep. Now I'm going to try to reshare. And now I'm going to go to my IDE. So while I'm moving this over to the new example, let me know if you cannot see this. So leave me a comment if, pepper me with comments if you cannot see the code that I'm trying to show you right now. All right, silence is golden, so that's good. So this implementation is going to demonstrate the use of C++ object-oriented programming, and it's going to be pretty cool. I still like object-oriented programming quite a bit, even though the world has largely moved on to purely generic programming for a variety of reasons, and we'll talk about that here in a second. So let me first show you the main program, and then we'll come back and take a look at the piece parts that it depends on. So what we're going to do here is we're going to use this abstract base class. So it's going to be our stack abstract base class. And this will allow us to write code that does not depend on the stack implementation. And that may appear mysterious and confusing at first, but believe me, I will explain it in great detail. So here's what it's going to look like, and then I'm going to show you how it works. So we're going to go over here, and we're going to make a call to a factory method called MakeStack. And MakeStack is going to be parameterized by a Boolean, which can be set at runtime based on the arguments we pass to the program here. And it's either going to make us a stack that uses a vector as the implementation, or a stack that uses a list as an implementation. So first and foremost, we don't know until runtime which kind of stack we're going to get. So we'll talk about how we accomplish that in a second. And we're going to get back from MakeStack a unique pointer, which will be a pointer to a stack. Now, what does that mean? Well, it turns out we're going to define an interface called stack here. And this interface is an abstract base class interface. So this version of stack is an abstract base class. How do we know it's an abstract base class, you ask? Well, let's take a look and see. First of all, you'll see it's parameterized by template T. So you can use generic programming with object-oriented programming quite nicely. You'll also see it's got overflow and underflow exceptions. So you can use exception handling quite nicely with object-oriented programming. And here's where things look different. Now we have got a bunch of methods, many of the same ones we saw before, except in this case, they've all been given this funny syntax at the end that says equal 0. What the heck is equal 0? Equal 0 is something that tells the compiler this method is a pure virtual function or a pure virtual method. And what that means is that there needn't be an implementation, but by the time someone actually goes ahead and uses an instance of this class, there must be an implementation. Otherwise, it won't compile. So we'll see how that works in a second. That's done through the magic of inheritance and overriding, and then dynamic binding is the vehicle by which the appropriate method is dispatched. Okay, so that's the high level. Abstract-based classes have at least one pure virtual method. In this case, we have a whole bunch of them. And you'll also notice that nowhere in this stack, abstract-based class, do we define any data members at all. So there's no private section, there's no data members, it's just defining the interface and the interface alone. Okay, so far so good. Now the good thing is you already know the semantics of stack, so it allows us to be able to write a lot of code without knowing or caring what the actual implementation is. And in fact, the way that object-oriented programming works from an implementation point of view is we don't have to know when we write the code what implementation will be used to implement this stack abstract base class. That decision will be deferred to runtime. Let's take a look and see how that works. So down here, we call this factory method that we'll look at in a second, and it makes us a stack pointer, and we stash that away inside of a unique pointer. So it's holding on this thing so that no matter what happens, if an exception is thrown, it's going to be deleted properly. And then we go ahead and write our code. So as you can see here, we're going to say stack push forever until we throw an exception. And that looks pretty much the same as we did before. The difference being that now we're saying SP arrow push, not SP dot push. And that, of course, is because we've allocated this to be a stack pointer, not a stack object. And I'll show you how that works when we look at MakeStack in just a moment. But otherwise, this code looks pretty much the same. It's got the try-catch block as before, aside from the fact we're calling it the push method through a pointer. Looks the same. Pop is the pop code is also going to be very similar with one small exception. Notice how every time through here we're going to say for each element in our stack, print the top element and then pop the top element. And I'm going to show you print top in a second. And notice what we do is we pass in the pointer to print top. So you'll see what that looks like. So SP was a unique pointer, and the get method returns that pointer. And so in many ways, that's just like your code that you're doing for your assignment 1 and 2, where you've got this get method that returns the underlying object that's being pointed to. But otherwise, other than that, it looks pretty much the same. And then the last thing we do is we're going to actually figure out what type of actual stack have we got. And I'll come back to that in a second. This is the part that deals with runtime type identification. So this is the RTTI portion of the code, but I don't want to get ahead of myself. So let's go over here and let's take a look at MakeStack and see what it's actually doing. So MakeStack is a factory method that's defined in this file. And this code says, if we're passed a Boolean that says use the VStack implementation, then call makeUnique to make us a new vector stack. V stands for vector stack implementation with this as the size of the stack. So if that value is set at runtime, then go make a vector stack implementation. Otherwise, if it's not set at runtime, go ahead and make an L stack. L stands for list stack. Now, what's interesting about this is you can see that VStack and L stack are both being created by separate calls to the makeUnique factory method. And that's coming back from MakeStack as a unique pointer to stack, not to VStack, not to L stack. Well, how is that possible? Well, it's possible because VStack and L stack are related to stack through inheritance. So the C++y way of saying that is that VStack and L stack are derived from the stack base class. If this was Java, we would say that VStack and L stack are extending the stack superclass, and they themselves would be subclasses. But the terms mean pretty much the same thing. Just C++ likes to use derived versus base, whereas Java and other languages like to use subclass versus superclass. So don't get worried if I sometimes slip and say subclass, superclass, but I should be saying derived class and base class because I'm in C++ mode at the moment. So let's go ahead and take a look at VStack and L stack. And I'm not going to focus on the implementation in detail at the moment. I want to show you the structure first, because that's the key thing to understand here to make sense out of object-oriented programming. So you'll see here is VStack. And oh, by the way, this is the inclusion guard technique that is important to know when you write header files or .cpp files that are templatized. So what we say here is if we come into this file and the symbol _v_stack_h is not yet defined, define it, and then allow all this other code to be included. And then if we re-include this header file again at some later point, then _v_stack, _v_stack_h will already be defined, and all the code in this file will be skipped. So this is what's often called a multiple inclusion header file guard. And make sure you do this when you write your code for your assignments. Otherwise, weird things can happen. Okay, so here we include stack.h, which was the abstract base class we saw over here. So that's been brought into the scope of VStack. And then what we say is we say class VStack, which is also templatized, inherits from, that's what the little colon does here, it inherits publicly from the stack abstract base class. And notice how it goes ahead and passes type T that it gets from its template type name down into the stack abstract base class. And of course, if you look there, you'll see that stack is also a template as well. So that's just forwarding it so it knows to be parameterized with the same information. And then what we do is for all the methods in stack that we had defined as pure virtual methods, all these things like push and top and pop and empty and full and so on, in VStack, we're now going to go ahead and override those methods, and we're going to provide them with their implementations. I probably should say override here, but I just haven't gotten to that point. So this is the interface. It's the same interface that we had in stack. It's that now we're actually going to define what those methods do. And in addition, we're also going to define what the implementation will be for VStack. And as you can see, as you might have guessed, VStack is going to be using the vector as its implementation. So we're going to define a vector of key to be the stack data member. And if we go look at the implementation of VStack, you can see that under the hood, we initialize that vector in the base member initialization section, giving it an initial size of 0. And then when we push, we're going to go ahead and check to see if we have to throw an exception or not. Let's say we don't. And then we go ahead and push the item to the end of the stack. That's what we do for the push that uses the const t ref. Then we also have another pushback that uses a t r value reference. And this uses the pushback method that will use that. That's the one that's defined on vector. And then you can see that we have top, and top will go ahead and check for underflow. If there's no underflow, it'll return the last element. And we have both const and non-const versions of top. Keep that in mind when you're implementing your assignment number 2, and you're going to have the 2 versions of the get reference, which works with, or two versions of the operator subscript that are going to be const and non-const. So use that as a model for that. Pop, as you can see here, goes ahead and checks for underflow and then does a pop back. And then empty and full do the obvious things, kind of forwarding to the right methods in the underlying vector. So empty on a stack turns into the vector's empty call. And as you can see here, we've also got the full method, which checks to see if the size of the stack is equal to the limit that we placed in the constructor up here. So that's how we can implement our vector stack. And as you can see, it abides by the interface that's defined with stack and then provides its own concrete implementation down here. So hopefully that helps to explain how VStack works. Now for kicks, let's go over and look at LStack. And LStack is pretty much the same idea. As before, we inherit from stack and we define all the methods, except in this case, rather than using a vector as the implementation, we're simply going to use a list. And in fact, if you take a look at the code here, it looks pretty much identical to the VStack version. It's just that it's using a different type of sequential container. And that's the beauty of these things. We can mix and match and plug and play, and everything works in a very clean and consistent and orthogonal way. So the principle of least surprise is clearly articulated here and works quite nicely. Okay, so let's go back now. Now that I've talked about the stack implementations for VStack and LStack and how they both conform to the stack interface, let's come back here and take a look at the main program again. And that'll give us a chance to dig a little deeper into how all these things are actually going to work under the hood. So you can see now that the MakeStack factory method is going to selectively decide whether to make a VStack or an LStack, and that'll be based on a Boolean parameter that's decided at runtime, literally. And then, as you're also going to see, that then triggers the use of the makeUnique factory method, and that'll either make us a VStack or that'll make us an LStack. So that's how we make the appropriate stack. But as you can see here, the way we use it, the code doesn't care which one it actually has. So that's very cool. Now let's go take a look at one other thing, because one of the things I told you before was when you use object-oriented programming, you can write code that doesn't care what kind of implementation it's going to get, and you can make changes, and that code that you wrote before, even the object code you wrote before, never has to be modified at all. And so let me show you an indication of how to do that. And the way to show that is through the PrintTop method. So let's go take a look at PrintTop. Here's PrintTop. This code is going to take a stack pointer, and I could have passed this in as a unique pointer. I just decided to do it as a naked pointer because it doesn't matter in this case. And what I'm going to do is I'm going to have this code. It's going to say top item equals, and then it's going to say SP arrow top. Now, what's interesting about this is this code is actually dynamically dispatched. And what I mean by that is that what looks like a call to SP arrow top is actually treated by the compiler as being SP, and then it's going to go ahead and follow the stack pointer through to its virtual pointer. So every object, you may recall when we talked about the history of C++, I mentioned that every object in C++ that has virtual methods has something called a virtual pointer or a V pointer, and that V pointer points to a virtual table or a V table, and the V table contains pointers to the methods that correspond to the virtual methods in the class. So if you go back and look at stack, for example, you'll see we have a whole bunch of virtual methods. We have the destructor, a couple of push methods, a couple of top methods, the pop method, and so on and so forth. And in this particular case, let's say for sake of argument that the top method here is method either 4 or 5. If you start counting from the beginning, depends whether you want to start counting from 0. I think it starts with 1. So the destructor would be the first method, push would be the second push would be the third, and then top would be the const top would be the fourth, and the non-const top would be the fifth. So let's focus on the non-const top, because that's what we're using here. And you can see over here when we come back, let's say for sake of argument, that's the fourth element in the virtual table, then stack pointer arrow V pointer points to the table of functions, and then the nth element, which would correspond to whatever number the top was here, that is going to end up being the pointer that's found when we index into that V table through the V pointer. And what comes back is a pointer, and then we go ahead and we dereference that pointer. So we're going to call that pointer. It's a pointer to function. It's going to be a function pointer. And then we're going to have the compiler pass in the stack object to that. So that's how the actual code gets dispatched. And what's cool about this is, as you can see, when looking at that code, you don't know, you don't care when you write the PrintTop method what the actual implementation of stack is. Is it the VStack? Is it the LStack? You don't know, you don't care, because all of this is done through indirection via the V table pointed to by the V pointer, which comes along as part of the stack pointer that's passed into PrintTop. So the nice part about this is you can compile this code, stick it off in a library somewhere at the binary level, and then start creating all kinds of new subclasses or derived classes of stack. And this code will never have to change, even though you have different implementations. And what's important to notice about this is when we create either the VStack version or the LStack version, that object we create will be set up by the constructor to have its V pointer point to the appropriate set of virtual methods. So obviously, the V pointer for VStack is going to point to the methods that are defined for the VStack implementation in that V table. Likewise, the V pointer for LStack is going to point to the V table that corresponds to the methods for the LStack implementation. And that's all handled magically for you under the hood by the C++ compiler using a variant of the Gang of 4 flyweight pattern. which basically means you move the state out of the object and put into a vtable. So a couple key things to notice here. This code could be totally generic. We can write that code, never touch it again. The MakeStack call here needs to be capable of being extended every time we come up with a new implementation. In this case, we're doing it through static binding, but you could also do dynamic linking to bring the implementations in if you were so inspired, using something called the component configurator pattern that appears in the Post-it2 book. So now what I'm going to do is I'm going to actually run the code and let you see what happens when it executes. And as you can see here, it behaved as you expected. It threw the overflow exception, it caught it, it popped the items off the stack, and it threw another underflow exception, it caught that. And at the very end, you can see it says configured with LStack. So how does it know that? And more importantly, can we change that? And can we change that without changing our code at all? And the answer is, of course, we can, because we're using object-oriented programming. So let's come back over here. And now let's go ahead and put just anything we want. Doesn't really matter what we put in here. We're just giving some argument so that the argument count is going to be greater than 1. And the reason it's greater than 1 is because there's always, the first argument 0 is always the name of the program. So anything else that comes after that will make the argument count greater than 1. So remember before, when we ran this program, it said LStack. And now let's go ahead and run it again. And this time, voila, it said configured with VStack. Notice how I didn't make any other changes to the code. I just changed the parameter passed in at the command line, just to make it be more than 1. And so what's happening here, as you can see, is that if argc is greater than 1, then we're going to use VStack. Otherwise, if it's equal to 0, or sorry, equal to 1, not greater than 1, we're going to use LStack. And that's exactly what happened. Well, how do we know this? Well, the last thing I want to show you in this example is the use of something known as runtime type identification, or RTTI. And as you can see here, what we do is we go ahead and grab the stack pointer from our unique pointer, and then we go ahead and do a dynamic cast. And we're basically asking the question, is this stack pointer a VStack pointer? And if the answer is yes, we print out configured with VStack. Otherwise, if the stack pointer is equal to LStack, then we've got an LStack. So dynamic cast is this mechanism that uses runtime type identification in order to determine whether or not the dynamic cast should succeed or fail. So if it turns out that we've allocated this to have a stack pointer that's an LStack, then it's going to say configured with LStack because the dynamic cast will succeed. Conversely, if we have it configured with a VStack, then the dynamic cast to VStack will succeed. And so we'll print out configured with VStack. So this is how we're able to determine at runtime the actual type of the derived object that we created based on the factory method that's up here. Okay, so those are the things I wanted to show you with respect to the implementation. Now what I'm going to do is I'm going to return back to the slides, hopefully, and we will get a chance to sort of talk about what we've learned and the pros and cons of this type of an approach. So hopefully you can all see the slides now. If not, let me know. So what are the benefits of doing object-oriented programming? So the benefits of object-oriented programming is we can reuse code without having to know the specifics of subclasses, either ones we built when we built the original code, or more interestingly, ones that we have come along and defined in the future. And the other thing you can see here is we can also write code that doesn't expose any implementation details, including the size of the objects at all to clients. In our particular case, we're always using a stack pointer in our code. So that code doesn't care the size of the actual implementation. Those things will be done in the derived classes. There's other techniques we can talk about later having to do with basically making use of the bridge pattern so that you have what's called an abstraction that always has a fixed size amount of space, typically just a pointer, and then it points off to the implementation. And we'll get into these patterns when we talk about the patterns discussion and the gang of 4 patterns later in the course. So these are some of the benefits of object-oriented programming. It kind of future-proofs your code because you can make changes and add things at runtime without knowing or caring about what changes, because they're all hidden from you by the magic of inheritance and dynamic binding. There are some downsides, however. One of the downsides is that some of those cool C++ optimization techniques we talked about, like member templates with variadic arguments, such as the in-place method that I've shown you, or the in-place back method that we talked about with vector and list and deck and so on. Those features don't work with virtual methods. So some of the templates, some of the more advanced template concepts only work with non-virtual methods. And again, that's by design. It's kind of the trade-off people make in order to use the more powerful and efficient generic programming techniques, is they can't take advantage of the virtual methods and the object-oriented programming features. So that's one thing to be concerned about. Not usually the end of the world, but just be aware that there's a bit of an optimization loss with the object-oriented features of C++. Another potential problem that it used to be a bigger problem and is not such a problem anymore is that whenever you have virtual methods in your code, they'll be dispatched using dynamic dispatching. And if you take a look at the link at the bottom of the page, you'll learn more about dynamic dispatching. And so what that means is that every object that's pointing to an object with virtual methods in it actually accesses those methods indirectly through the V pointer and the V table. So if you take a look, for example, our VStack implementation would contain the pointer to the V table, the member that keeps track of the top and the stack, and the pointer to the V table would point over to, that's called a V pointer. The pointer to the V table, which is the V pointer, will point to the virtual table of the stack, which will then contain all the methods for push and pop and top and so on and so forth. And so all the access to these methods, to these virtual methods, will be done indirectly. So that means, for example, that the inlining optimizations that C++, especially its generic programming features, are so widely known for, that won't be achievable or usable. And there also is just a little bit of extra overhead typically when doing virtual method dispatching, because you have to go indirect to a pointer, go find a pointer to the function in a vtable, and then invoke it. Now, it turns out that modern compilers optimize the heck out of this stuff through various techniques like adjuster thunks and other optimizations. So the actual overhead is insignificant in practice. Probably the bigger overhead is just the fact that some of the inline optimizations cannot easily be done if you program through pointers to base class objects as opposed to using derived class objects directly. And of course, the whole point of object-oriented programming is to be able to access these derived objects through pointers to base objects. So that's the end of our object-oriented stack implementation. What I want to do now in the last few minutes in the class is just kind of wrap up and summarize what we've learned over this introductory part. And first thing is that clearly a huge contribution of C++ over alternatives like C is its support for abstract data types and generic programming. So hopefully you have a much better feeling for classes, parameterized types, and exception handling. And these are the kinds of things you should be using all the time in your code as you write more and more non-trivial C++ codes. And we'll get a chance to do that later in the class. For other types of programs, or for some other types of programs, C++'s support for object-oriented programming is very important to be able to write highly extensible and highly flexible software. And these, of course, include things like inheritance, dynamic binding, runtime, type identification, all the stuff we just talked about. It's not necessary for everything, but when it is useful, when it is necessary, it's very, very useful. And so that again is important. It's important at the very least to know these concepts. If for no other reason, if you program in other object-oriented languages like Java, these concepts are front and center to the way in which those languages are designed and implemented. So Java is more of an object-oriented language in many ways than C++ is, because they don't give you as good support in Java for generics and parameterized types and so on. Although, of course, Java is moving rapidly into the functional programming world at a rapid clip, which is a topic for a whole other class. So, but for the vast majority of C++ programs being written today by people who are aware of C++ and its modern programming paradigm support, generic programming is really the crown coin of the realm. It's really the thing that people most likely are emphasizing and applying when they do modern C++. So even though you're always welcome to do the object-oriented features, and there are times when it's very valuable to do so, generic programming is really the primary design center of the C++ programming language going forward. In our class, we're going to be talking about all these different paradigms. Your assignments will give you practice with multiple paradigms. And in fact, you'll see that for many things we're going to be doing, we're going to be mixing generic programming with object-oriented programming for good effect. But be aware that you need to become an expert at both of those things in order to be considered really a top-notch C++ developer these days.